All right, welcome to this explainer. Today, we're diving straight into the fascinating three-dimensional world of solid-state chemistry. We're going to take a journey from the macro properties, the stuff you can actually see and touch, all the way down to the microscopic lattice geometries and atomic imperfections that literally make our modern technological world possible.
To kick things off, have you ever looked closely at the glass windows on really old historical buildings? You might notice they look kind of warped, like they're noticeably bulging at the bottom edge. Well, it's not just some weird manufacturing quirk from the past, it's actually science happening in incredibly slow motion, and it completely challenges our fundamental understanding of what a solid actually is.
Here's the wild part. Glass is essentially a supercooled liquid. It is what we call an amorphous solid, a term that literally means without form. Because it lacks the long-range internal structural order that we usually associate with solid matter, it has this secret fluidity. Over decades and decades, gravity just slowly pulls it downwards.
So, here's our roadmap for the explainer. We'll be hitting 1. The nature of solids. 2. Types of crystalline solids. 3. Lattices and unit cells. 4. The geometry of crystals. 5. Inside with Bragg's equation. And finally, 6. Crystal defects and properties.
Section 1. The nature of solids. Order versus chaos.
Looking at the big picture, solids generally fall into two main buckets. On one side, you've got crystalline solids. These are your true solids. They have perfectly repeating, long-range geometric order. And because their bonds are completely uniform, they break at a very sharp, specific melting point. They're also anisotropic, meaning their physical properties actually change depending on the direction you measure them. On the flip side, amorphous solids, like our window glass, lack that perfect internal structure. They just melt gradually over a range of temperatures and behave isotropically, meaning they're basically the same in every direction.
Section 2. Types of crystalline solids. The building blocks.
Zooming in a bit, how are these crystalline solids actually held together? Well, the binding force is everything. It totally dictates a solid's melting point and its conductivity. Ionic solids rely on strong electrostatic forces, pushing their melting points extremely high. Molecular solids are bound by weak van der Waals forces, think dry ice, so they melt super easily. Metallic solids feature delocalized electrons, which is exactly why they conduct electricity so well. Meanwhile, covalent network solids, like diamonds, are tightly locked up and act as pure insulators.
Section 3. Lattices and unit cells. Mapping the invisible.
Okay, we're stepping into the micro world now. Nature plays by some pretty strict spatial rules here. By tweaking just the lengths of the edges and the angles between them, we get 7 basic crystal systems. From there, we derive exactly 14 possible Bravais lattices. These are the fundamental underlying geometric frameworks that dictate the shape of literally every single crystal in existence.
To make sense of all this architecture, we use something called a unit cell. It's the smallest repeating portion of a space lattice. Think of the space lattice as a massive, incredibly complex brick wall. The unit cell, that's just one single brick. If you completely understand the dimensions and angles of that one brick, you instantly understand the architecture of the entire infinite structure.
And these microscopic bricks have amazing symmetry. It's like perfect atomic origami. A crystal can have a plane of symmetry, which acts like an internal mirror, flawlessly dividing it into 2 identical halves. Or it can have a center of symmetry, a single imaginary dot right in the middle, where any straight line drawn through it hits identical boundaries on both sides. It is perfectly balanced.
Section 4. The geometry of crystals. Packing efficiency.
All right, here is the ultimate solid-state puzzle. How do you pack spherical atoms as efficiently as humanly possible? If you just stack them on the bare corners of a cube, what we call a simple cubic structure, you end up wasting almost half the space. It's only 52% efficient. But if nature packs atoms into the center of the body or onto the center of the faces, everything tightens up. Face-centered cubic structures actually hit a maximum packing efficiency of 74%.
The logic behind how we calculate the number of atoms inside these unit cells is super clever. You see, an atom sitting right on the corner isn't fully inside that one cell. It's acting like a joint, shared equally by 8 different cubes touching that corner, so it only counts as 1/8 of an atom for our cell. An atom sitting flat on a face is split by 2 cubes, contributing a half. This brilliant 3D accounting proves that a face-centered unit cell holds exactly 4 complete atoms.
Section 5. Inside with Bragg's equation.
Now, you might be wondering, how do we actually know all this geometric math is true? We can't exactly stick a tiny ruler inside a diamond, right?
Well, Max von Laue and the Braggs figured out they could use X-rays to literally look inside solids. Because X-ray wavelengths happen to be almost perfectly identical to the physical distances between atomic layers, firing a beam into a crystal causes diffraction. By mapping how the rays bounced back and synchronized, they could calculate the exact invisible distances between the layers.
This equation was an absolute game changer. By simply measuring the angle of maximum X-ray reflection, scientists decoded the exact 3D blueprints of things like sodium chloride. Bragg's equation wasn't just neat theory, it gave us the ability to build X-ray spectrometers. This is how humanity definitively proved the internal face-centered lattice of common table salt, all without ever having to actually see the atoms.
Section 6. Crystal defects and properties. The perfect imperfections. Let's flip the script for a minute. Nature is rarely perfectly tidy. So what happens when there are mistakes at the subatomic level? In ionic solids, we get stoichiometric defects. These don't change the overall chemical formula, but they absolutely alter the physical reality of the crystal. The crystal ratio stays the same, but the internal architecture takes a hit. The two most famous offenders here are Schottky and Frenkel defects.
To put it simply, imagine a movie theater. A Schottky defect is like a pair of people completely leaving the theater. The overall density of the room goes down. But a Frenkel defect, that's like someone getting out of their seat and just standing awkwardly in the aisle. The atom is misplaced into an interstitial space, but the overall density of the crystal stays exactly the same.
These tiny structural shifts are a really big deal, especially for electricity. It all comes down to the energy gaps between bands. In conductors, the valence band overlaps with the conduction band, so electricity flows effortlessly. Insulators have massive gaps that electrons just cannot cross. But semiconductors, they have a very small gap. And it's actually by introducing controlled defects, a process called doping, that we bridge this gap and tell electricity exactly when and how to flow.
And here is where a defect officially becomes a feature. Sometimes an empty space in the lattice gets filled by a stray, trapped electron. We call this an F-center. And guess what? That trapped electron absorbs specific visual wavelengths of light. F-centers are the secret ingredient that gives crystals their brilliant, vibrant colors. Without these microscopic mistakes, most of those beautiful crystals you see in nature would just be totally clear and, honestly, kind of boring.
It's a similar story for magnetic properties. A solid's magnetic personality is completely dictated by microscopic tugs of war between its internal electron domains. If domains naturally align perfectly together, you get a strong ferromagnetic permanent magnet. If they align in perfectly opposite directions, they cancel each other out entirely into an antiferromagnetic state with zero pole.
So, to wrap up this explainer, I want to leave you with a thought. We spend so much time studying the flawless, perfect order of the crystal lattice. But given that defects are what create semiconductors, generate amazing colors, and alter magnetic states, are the so-called flaws actually a crystal's most valuable feature? The next time you look at a colorful gem or use the microchip in your phone, remember, it's not perfection making it possible, it's highly structured chaos. Thanks for hanging out with me for this explainer.